Okay, in today's lecture, we're going to cover the first part of the section 11.5 material on techniques for finding derivatives. So we had introduced the idea of a derivative in the last section as a function which represents the slope of the tangent line to the graph of a function at any point on the curve. And we had seen the definition of the derivative in terms of a limit. In particular, it was the limit of a difference quotient of the function as h approaches 0, as long as that limit exists. Now, in this section, we're going to start talking about some techniques which will make finding derivatives much easier, where we no longer need to rely on that limit definition of derivative, which we saw in the last section can be pretty time-consuming. So the first rule, or technique, which we'll discuss for finding derivatives is known as the constant rule, which says if our function f of x is equal to some constant k, which is a real number, then the derivative of that constant function is 0. So that is, the derivative of any constant function is 0. Now we can show that by using the limit definition of the derivative, or if we make use of a more intuitive approach, let's say that we consider the graph of some constant function in the xy plane, perhaps the graph of y equals k, which would be some horizontal line passing through y equals k. So the tangent line to this graph would be the line itself. So the slope of that tangent line, which is our derivative, would be 0 because the slope of a horizontal line is 0. So let's look at some examples making use of this constant rule. So in the next few parts, we're asked to find the derivative of each function. And in part A, we have f of x is 20. Now 20 is a constant, so the derivative of this function is 0. In part B, we have y is equal to pi squared. Now remember, pi is just some number, so taking the square of that value is still just some constant. So the derivative of y, which we might write as y prime, is equal to 0. So recall, if we have a function defined as y in terms of x, its derivative can be denoted as y prime. Now in part C, we have f of t is equal to negative e to the fourth. Now e is just a real number, so taking negative e to the fourth is still just some real constant value. So the derivative of this constant is still 0. And in part D, we have y is pi to the 100th power divided by 16, which is still just some constant since pi is constant. So the derivative, y prime, is 0. So derivative of any constant function we now know is 0, regardless of what the constant is. Now the next rule that we'll talk about is one which we'll use probably most frequently, and is called the power rule. Now the power rule says if we have a function of the form f of x is x to the n, where any n is any real number, then the derivative of that function f prime is given by n times x to the n minus 1. So that is, the derivative of x to the nth power is found by multiplying the exponent n on the original function by a power of x that is 1 less. Or in other words, we can think about our function f of x as x to the n. So this power rule says to find the derivative of that function, we take the exponent n and we pull it out in front of our variable x, and then the power of x is reduced by 1. We subtract 1 from whatever the power was. So let's look at some examples of this. So in part A, we're asked to find the derivative of f of x, which is x to the fifth. So using the power rule, we have f prime of x would be 5 times x to the 5 minus 1 power, or 5x to the fourth power. In part B, we have y equals x to the 13th. So using the power rule, y prime would be 13x to the 12th. So we bring down that power 13 out in front of our variable x, and we decrease the power of x. So let's look at another one. In part C, we have f of t is t to the 5/4 power. So here, instead of using the variable x, we're just using t, but the power rule is the same. The derivative of this function, f prime of t, would be 5/4, so we pull the power out in front of our variable t, and then the power was 5/4, and we're subtracting 1 from that value. So we have 5/4 times t to the 5/4 minus 1 is 1/4. Now in part D, we have y is 1 over x to the fourth. So this may not look like a function where we could use the power rule at first, but recall that 1 over x to the fourth can be rewritten as x to the negative fourth power. So remember, in general, a notational rule that we can make use of is that if we have some variable and we're raising it to a negative power, that's the same as taking 1 over x raised to that positive power. So by rewriting 1 over x to the fourth as x to the negative fourth, we can make use of the power rule, which says that our derivative, y prime, would be negative 4 times x to the negative 5 power. Or if we want to rewrite this, we can think of this as negative 4 times, well, x to the negative fifth is the same as 1 over x to the positive 5 power. So we could also write this as negative 4 divided by x to the fifth power. Now in part E, we have something similar. Y is the square root of t. So again, at first it looks like we may not be able to apply the power rule, but recall that these radical expressions, like the square root of t, can be rewritten as fractional exponents. So the square root of t would be t to the 1/2 power, or more generally, if we have the nth root of some variable x, we can write that as x to the 1 over n power. So we're going to make use of this a lot throughout our courses. So these last two examples, parts D and E, we're making use of some notational fact about exponential functions in order to simplify finding our derivatives. So here, y prime, using the power rule, would be 1/2 t to the 1/2 minus 1, which would be the negative 1/2 power. Or we can rewrite this as 1/2 times. Now t to the negative 1/2 is the same as 1 over t to the 1/2. Or this is the same as 1/2 times, in our denominator, that t to the 1/2 is the same as square root of t. So taking our product, we have a derivative of 1 over twice the square root of t. So it's useful to remember in this course that the derivative of the square root of a variable, say square root of x or square root of t, is 1 over 2 times the square root of that variable. All right, so a few examples with the power rule. Now the next rule, which we'll make use of, is called the constant multiple rule, which says the following. If we have a function f, which is differentiable, so its derivative exists, and k is some constant, then the derivative of a constant times the function f of x is equal to the constant k times the derivative of that function. In other words, you can pull a constant out in front of the function that you're taking the derivative of. All right. Now a little bit of a reminder here. Recall that this notation, d dx of a function, is used to denote the derivative or differentiation of that function. And that notation, remember, is called Leibniz notation for the derivative. So, in this next example, we're asked to find the derivative of each function. So in part A, we have f of x is 12 times x cubed. Now using the constant multiple rule, our derivative, f prime of x, well, we have 12, and then we're going to multiply by the derivative of the function that came after that 12. So the derivative of x cubed is 3x squared using the power rule. So now we have 12 times 3x squared, which is 36x squared. Now sort of an easier way to consider this constant multiple rule is the following. When we apply the power rule here, we take the exponent 3 and we bring it down in front of the power of x. So from here on out, whenever we bring the power of x out in front of our function by using the power rule, we're going to immediately multiply by whatever constant appeared in front of that function. So rather than writing it as 12 times 3x squared, whenever I pull down that 3, I'll immediately say, well, 3 times 12 gives me my 36, and then decreasing the power of x by 1, we have x squared. All right. So in part B, we have f of, this should be f of x, is 30x to the 7th. So our derivative, f prime of x, using the constant multiple rule and the power rule, well, when we pull down the 7 from the power of x and multiply by the constant 30 out in front, we have 210 times x to the 6th power. Now in part C, we have y is 5 times the cubed root of x. And remember, when we're dealing with these radical expressions like the cubed root, we might first rewrite them in terms of fractional powers. So we could rewrite this as 5 times x to the 1/3 instead of the cubed root of x. And now, using the constant multiple and power rules, well, when we pull down our power of 1/3, we have 5/3 times x to the 1/3 minus 1 power, or 5/3 times x to the negative 2/3 power. Or if we want, instead of using a negative power here, we can write this as 5/3 times 1 over x to the positive 2/3, which is the same as 5 over 3 times x to the 2/3 power. All right. And in part D, we have y is equal to negative 10 divided by t squared. So rewriting this, that is the same as negative 10 times t to the negative 2. So instead of writing it as division by t squared, we can write it as multiplication by t to the negative 2. And then using the power rule and the constant multiple rule, when I pull down the constant of negative 2 and multiply by my negative 10 out in front, I'll have a positive 20 times t to the negative third power. Or if I want to rewrite this using positive powers, this is the same as 20 divided by t to the positive third. All right. Now, the next rule that we'll look at is known as the sum difference rule. And here's what it says. If we have two functions f and g, which are differentiable, that is, their derivatives exist, then the derivative of the sum or difference of those two functions, f plus g or f minus g, is equal to the sum or difference of the derivatives of those functions. That is f prime of x plus or minus g prime of x. So this means that the derivative of a sum or difference of functions is equal to the sum or difference of the derivatives of those functions. So this is frequently used when we're differentiating polynomials or sums or differences of power functions. So as an example, in part A, we have f of x is this polynomial. So using the sum difference rule to find the derivative of this function, f prime of x, I can take the derivative of each term one by one, and then take the sum or difference of the derivatives of each of those terms. So starting with my first term, 12, well, 12 is a constant, and the derivative of a constant function, we said, is 0. Then I'm subtracting. I have my next term as 6 times x, which is a linear function. It represents a line of slope 6. And remember, in the last section, we said the derivative of any linear function is just the slope of that line. So here the derivative of 6x would be the slope of that line 6. Plus, for our next term, we have a 7x squared, which using the constant multiple and power rules would have a derivative of 14x to the first power. And then we're subtracting the derivative of our last term, 10x cubed, which using the constant multiple and power rules would have a derivative of 30x squared. So simplifying the way that we've written this a little bit, we have f of x is negative 6 plus 14x minus 30x squared. So the sum difference rule allows us to differentiate each term of this function individually and then take the sum or difference of the derivatives of those individual pieces. So let's look at part B. We have 5t to the 8/7 plus 5 times the square root of t. So I might start by rewriting the square root of t as t to the 1/2 power. And now using the sum rule, the derivative, y prime, would be found by first differentiating 5t to the 8/7, which would be 40/7 times t to the 1/7. When I take 8/7 minus 1, that leaves me a power of 1/7. And then plus the derivative of 5t to the 1/2 would be 5 times 1/2, or 5/2, t to the negative 1/2. Or we could rewrite this as 40 over 7 t to the 1/7 plus 5 over 2 times the square root of t. Okay. So let's look at another one. In part C, we have f of t is 4 over t minus 2 times the cubed root of t squared. So for this one, it looks a little tricky at first, but if we rewrite this, it's not so bad. So starting with the first term, 4 divided by t, we can rewrite that as 4 times t to the negative 1 power. And then we have a minus 2 times the cubed root of t squared. Now remember, the cubed root is the same as the 1/3 power, so the cubed root of t squared would be the same as t squared to the 1/3 power. Now if I rewrite this another way, I have 4t to the negative first, and the expression t squared to the 1/3 power. Well, remember properties of exponentials. If I have a power which is being raised to some power, I can write that as a single power function where my exponent is the product of those powers. So here 2 times 1/3 would give me the 2/3 power. So now this looks just like the other problems that we've been working with. So using the difference rule here, f prime of t can be found by first taking the derivative of 4t to the negative first, which would be negative 4t to the negative 2, minus the derivative of 2t to the 2/3, which would be 4/3 t to the negative 1/3. Or if I want to rewrite this using positive powers, I could take this as negative 4 divided by t to the positive 2 minus 4 divided by 3 times t to the 1/3 power. Or if you want this t to the 1/3 power in the denominator, you could rewrite as the cubed root of t. So we find this expression for our derivative. Now in part D, we have y is the quotient of two polynomials. We have 12 minus 7x plus 6x cubed all over x squared. And so far, we haven't talked about a rule for finding the derivative of a quotient of functions. We'll introduce that in our next section. So in order to handle this, we would have to rewrite this function in a way so that it's not a quotient. Now I know that I could rewrite this in the following way. I could split this fraction as 12 divided by x squared minus 7x divided by x squared plus 6x cubed divided by x squared. Or if I simplify this a little bit, y could be written as 12 times x to the negative 2. In my second term, I have an x divided by x squared. That's going to leave me x to the first in the denominator. So I've got minus 7 divided by x, or 7x to the negative first power. And then plus, for my last term, I have x cubed divided by x squared. If I cancel 2 powers of x, that leaves me x to the first in the numerator. So I just have 6x. And now this looks like the examples that we've done in parts A through C. So using the sum difference rule, our derivative y prime would be given by negative 24 x to the negative third plus, so when I bring down this power of negative 1 and multiply by the negative 7, I get a positive 7 times x to the negative 2, then plus the derivative of this linear term on the end, 6x, is just the slope of that line, which is 6. So we have the following expression for our derivative, or if you want to rewrite it using positive powers, this is the same as negative 24 divided by x to the third, plus 7 divided by x squared plus 6. So that would be an equivalent way to write your answer using positive powers. Okay. So now that we have these techniques or these simple rules for finding derivatives of some basic functions, let's look at an example that's similar to what we saw in the previous section. We want to find the equation of the tangent line to the following curve at x equals 1, and then express our answer in slope-intercept form. Now, before we had the rules that we've discussed in this section, we would have had to find the derivative, which is the slope of our tangent line, of this function, using the limit definition of derivative. So I would have to replace all of my x's by x plus h's and then expand everything. It becomes a huge amount of work here. But now that we have rules for differentiating these functions, the problem is much easier. So to find the equation of a line, there's two things that we need. The first is a point that lies on our line. Now we're given the x-coordinate for our point here is 1, and to find our y-coordinate, we're going to look at the equation for y in terms of x. So in this example, if x is equal to 1, then our y value, well, if I plug in 1 for x, we have negative 1 plus 4 minus 2 plus 2. So we're left with 4 minus 1, or 3, for our y value. So this line is going to pass through the point 1, 3, and we need the slope of this line. Now the slope of the tangent line to a curve is the derivative. So here we can find y prime by using the rules which we've discussed so far in this section. So using the sum difference rule, we find the derivative of y would be negative 5 times x to the fourth plus 8x to the first minus 2. And then plus our term on the end is a constant 2, and the derivative of any constant is 0. So here I don't need to write my plus 0 on the end. So this is the slope of my tangent line, and we're interested in the slope at a specific value of x, namely when x is equal to 1. So here, if x equals 1, then let's look at what our slope, y prime, is. So plugging in 1 for x, we have negative 5 plus 8 minus 2, or 3 minus 2, which would be 1. So making use of point slope form, the equation of this line would be given by y minus the y-coordinate, which we found to be 3, is equal to our slope, which was 1, times x minus the x-coordinate, which was 1. So solving for y, we have y minus 3 is x minus 1, So y is equal to x, and adding 3 to both sides, we get y is x plus 2. So we see in this example that now that we have these rules for finding derivatives of functions more easily, this problem of finding the equation of the tangent line to a curve is not nearly as difficult.